Okay, let's get started with the exercises then. Right. So the first relation is essentially saying that two points in the plane are equivalent if they lie on the same parabola, right? Parabola, whatever. And y minus x no x square happens to be the constant. Basically, that's separating them, right? It's a different y coordinate. That's the origin, and that's shifting. So that's what the equivalence relation is trying to say. And let's prove the properties. So let's see. Yeah. So yeah. So if the same point, what is up with the same point? Let's see, x comma y and x comma y. So it's not proven yet because we haven't really defined squaring and plus, but we soon will. And x square plus minus y is equal to x square minus y. So therefore, it's reflexive, right? What about symmetry now? Well, x comma y is equivalent to okay, so it's an ordered pair, right? Ah, yeah, it's a bit confusing here. Uh-huh. So x comma y is equivalent to, let's say, z comma w, right? Okay. Yeah, so given that this is an actual equality and an actual equality is also an equivalence relation and follows the properties, transitivity, reflexivity, and uh, symmetry, we can just use the symmetry of equality to work this out. So what does that mean? That means x square minus y is equal to z square minus w. And it works both ways. So because of that, we can also say, just write down z square minus w is equal to x square minus y, and that's the reverse, right? And same thing with transitivity too. We're just using the equality's transitivity ultimately. Yep, so it's an equivalence relation. Anything else? Uh, Describe the equivalence classes. Yeah, that's what I first did. Okay. Yes, show that the restriction of an equivalence relation is also an equivalence relation. It is a property we will be using in the next one. So I attempted a few problems on the next section, and yeah, we will be using it there. Okay, so C naught is a subset of C. So if yeah. Now, so first one, for all x belongs to C naught now, x, uh, I think it's directly true because, this implies this and this implies this by reflexivity of C, right? Because tilde is so what does the restriction mean? Hang on, the restriction is defined, right? Yeah, it's intersection that. So since x belongs to C naught, x, hang on, is it A naught or C naught? Oh, there was no C naught. Okay, sorry. All right. C is the restriction of that. Yeah, there's no symbol given, is it? Yeah, there's no symbol given. So restriction of this is equal to C naught. All right, new symbol. Yeah. So x belongs to A naught. So that means x comma x definitely belongs to A naught cross A naught, right? And x comma x belongs to C because x is reflexive. So x belongs to both of them. So ultimately, it's an intersection game now, right? Okay, x comma y belongs to A naught, right? So what does that mean? That means x comma y and y comma x both belongs to A naught cross A naught, correct? Now, do they both belong in C? Yes, they do because C is defined on A, and this is always true by a subset. So A naught is a subset of A, belongs to A, not yeah, A. So this is true by definition of this and Cartesian product. And X, uh, this is defined on C and also well defined on C naught. So that's one thing to check. It's well defined on C naught because X and Y are both in A naught cross A naught. So once we do that, then we can check for actual reflexibility, transit symmetry, and that's true because C is so, right? Okay. So same thing, we have to check for transitivity here, and since X comma Y comma Z are in A naught, same argument, all the triplets are in A naught cross A naught, and by transitivity of C, it's there. So it's going to be in the intersection, and because of that, it's going to be in the restriction. So exact same argument. So in general, quite a few relations would be such that if you respect them, you'll be fine. Uh, but yeah, you'll have to think of some good criterion, criteria. Never mind. Yeah. Okay. Yeah. The problem with the proof. Yes, there is a very simple problem with the proof, and it assumes that there exists a B such that A B. Right. There is absolutely no. Oh wait, I used tilde for C. Sorry about that. Yeah, I just realized that now. That's tilde and tilde not if you want, you know. Sorry about that. Yeah. Why should there exist such a B? Why? Right? There is absolutely nothing, you know, that makes our assumption true. So the implication is fine. This may be a stronger or weaker condition than reflexivity, and I'm not sure. It certainly implies reflexivity, so it's certainly a bit stronger, weaker at least, right? Hang on, let me think. Stronger means stronger condition. Yeah, so it's weaker or equivalent because if reflexivity implies it, then it's equivalent, and if reflexivity doesn't, then it's weaker. Yeah. So because we don't have this assumption, okay, yeah, just forget about the stronger weaker thing. Yeah, because of this assumption, which need not be true, because you could have the equality equivalence relation, and the only equivalence classes for of equality for the real line are all real numbers in discrete bits. So because of that, all that's left is essentially we only have A is equal to A, nothing else, right? Nothing else. So yeah, this assumption is satisfied by A, but we never we never took it to be true. That's the problem. Okay, A is equivalent to A. Yeah. So this trick is question 4 is going to be important when we discuss quotient groups, and this trick is used all the time in group theory because essentially it's like a kernel. So A naught equivalent to A1 if and only if f of A naught is equal to f of A1. So a way to visualize is it is so let's take the floor function of real numbers, right? So what does that mean? That means 0 comma 1 all becomes 0, and 1 comma 2 all becomes 1, and so on, right? And so yeah, a bunch of things can collapse to a point essentially. That's the beauty of it. So any surjective function, so it has to be surjective and in the domain can be defined, right? So that this is an equivalence relation. Okay. So so f of a naught is equal to f of a naught by well, because if it's not, then it contradicts the rule of assignment, right? It's a unique thing. What else? F of A naught is equal to F of A1 implies F of A1 implies F is equal to F of A naught. So it's symmetric. And by the same property of equality, it's also transitive. Okay. Yeah. Let A star be the set of equivalence classes. So think of them as we can take a representative of each equivalence class. So we can take all the integers, and that would some look like our modulo Z if you've seen it, something like that. But anyways, these are the equivalence classes. It's a partition of the set A, and we want bijective correspondence between A star and B. So is it surjective? Let's see. F is a surjective function. So, hmm, so okay. So for all, since A is, yeah, this is a partition, right? So for all B and B, there exists an A in A such that F of A is equal to B, right? This is surjective. Now, this A must lie in some element of A star because it's a partition. And therefore, it's a surjective function because we can just take the entire set and map it to the same B, right? So if we choose the A in A star, not A, let's call it D in A star, and D goes to this B. And since all of the A's in D will go to B, they'll be fine. So that's the bijective. We're defining a bijective correspondence ultimately, right? So using this, we've gotten a surjective function. Is that correct? Yeah. Now we have to show that it's 1, 1. For so we have to show that f of d1. So keep in mind this. Okay, I'm going to call it g now. Keep in mind this is a function from a collection of elements to an element. This is not, so it's kind of a set function. It's not exactly a regular function like we've seen before. So g of d1 is equal to g of d2, right? Okay. So now we choose, so we have to show that d1 is equal to d2. And this is quite simple because we just choose an A that's in D1, right? And then A in D2. So A1 and A2. And we take the function A uh, on it. And they're both going to be equal to the same thing, B, right? Why? Because that's exactly how we've defined it. That's the exact map I wanted to define. So A1 is equal to A2. Now, what does that mean? That means A1 is equivalent to A2. And given the theorem we just proved, since D1 and D2 have a they're the same they're a non-disjoint equivalence class, right? Because they have a member that's equivalent. You can just extend the proof. So D1 ends up being equal to D2. So it's injective. So that means we got a bijective correspondence from the set of partitions to B. And yeah, we're defining it using the original function. All right. Cool. Now question 5. Huh. hmm hmm I'll have to write it down. Let's see. Y minus x is an integer. Y is equal to x plus 1. X is greater than 0, less than 2. That goes from 1 to 3. Okay. So these are subsets of the plane, and we have to show that they're in equivalence relation on the real line. Hmm. I'll try to graph them. That would be a good idea. Okay. So y minus x is an integer. When is that happening? Okay, so y is here, x must be, so this, when is y equal to x? Y is equal to x here, and so that's one integer, and looks like that. Hmm? Okay, so we just get a bunch of lines, right? Is that it? So what does that mean? That means y is shifted by x here. Yeah, yeah. So it looks like a set of lines like that. And what about this one? Y is equal to x plus one. Yeah. So I believe it's an entire area like that. Hmm. Okay. Yeah. So I think I'll have to think about it. So yeah. So I took a break. Let's see. So first, I'll just try showing that both of them are equivalence relations, and then we'll go from there. Do I have to show both of them or just one of them? Just that one. Okay. Yeah, because the other one doesn't make sense as an equivalence relation actually. What this actually is just so let's say this is y is equal to x. So which one is y is equal to x plus one? This one, right? Yeah. And from zero to that's it, right? Did I mess them up? Is it? Yeah. All right. So it's kind of clear visually that S prime is a superset of S. Yeah. So I'll try showing that. And okay, this directly follows because well, so what does this mean? This is and, right? Uh, Even if this is just a restriction on this, it's fine. Yeah, so it ultimately comes down to y is equal to x plus 1 and x between 0 comma 2 implies y minus x belongs to z. And this is too simple of an algebra problem, which you can do after maybe the next section if you want. But yeah, given this, this subset is clearly done. Now you have to show it's an equivalence solution. All right. So let's first go with reflexivity, let's say. So x minus x, right? That's what it is. Yeah, x minus x is 0, which is an integer, so we're done. Y minus x is an integer, so x minus y is a negative of an integer, which is also an integer, so it's an integer, so yx is also there, so it's symmetric. And the difference of two integers is basically, y minus x is an integer and plus uh, z minus y is equal to z minus x. So this is an integer, this is an integer, this is an integer, therefore this is an integer, and therefore z minus x. So it's transitive as well, right? Yeah, so it's an equivalence relation. Next one, yeah, given any collection, it's an extension of the restriction problem. So what does that mean? That means x comma y comma z belongs to intersection a bunch of equivalence relations. Oh wait, yeah, this is not. So they're all in the same set, I presumably, right? So it's the ordered pairs. Okay. So since all of them are equivalence relations, all of So is it safe to say for all x comma x belongs to intersection? So it belongs to all of them, so it must belong to the intersection. So that's fine. Yeah, I'm just calling this the intersection, which is weird, but whatever. Uh, this, so this must belong to the set A, right? Hang on, I have to check the intersection thing. Okay, it's the same set, yeah. So x comma y must belong to the intersection, right? That's the case. So it must be true in all of them. And given that it's true in all of them we can apply symmetry, and because of that, in all of them, x comma y belongs to that. So you'll have to use the quantifier argument from the arbitrary intersection, right? From question 6. That's what we're using here. I'm just saying it now because yeah. Given that it's in all of them, it's going to lie in the intersection as well. And yeah, pretty much we can extend it to transitive as well. Let's see. So this is belonging in all of them. This is also belonging in all of them. And we can use the transitivity of all of them to get this is in all of them. So we're done. Okay. Okay. So all the equivalence relations of the real line that are the intersection of S. Okay. So is S let's see. Intersection of all equivalence relations on the real line that contains S. So S is S an equivalence relation for all equivalence relations that contain the relation S. Okay. Hmm. So how could I describe it? Let's see. So essentially S must be contained in this. So this is a subset of y is equal to x plus 1 from 0 to 2. And they were lines, right? Hmm. So all of them must have it. So one thing I can think of is you take y. Okay, must it have an integer? So y minus x belongs to L. Hmm. I'll have to think again. Okay, so I'm not 100% sure of this. I would like to be corrected, but whatever. Yeah, I suspect the intersection is S prime itself, right? So S prime is an equivalence relation that contains S, and yeah, so its intersection must be contained in S prime, right? Now, if S prime is the thing, then what? So yeah, so what number can it be? Okay, so y minus x must absolutely be an integer, right? So it can't be a bigger set. If it's a bigger set, then f prime is going to shorten it. So it can only be a subset of z, right? Okay. And yeah, so one is certainly going to be in because so y minus x certainly will belong to the set containing one. That's certainly there, right? Because it contains x, right? Now, I think we can show by transitivity that it might contain 0 too, or maybe just one. Let's see. So let's say y minus x is equal to 1 and x minus z is equal to 1. So what does that mean? Y minus z is equal to 2, right? Okay. So that means every natural number can be achieved this way. So by pure induction, I can get essentially Z plus, right? Okay, now can I get every negative number, right? Let's see. So, oh, right, we have to exploit symmetry here and reflectivity. So, yeah, since it has to be reflexive, y minus x must be at least some number, let's say 1, and x minus y has to be some number, 1. Now, if we add them together, we get 0 is equal to 2. So, what does that mean? That means 0 must be in the set, right? If 0 is not in the set, we'll have a problem. Yeah, it's bad. Right. Yeah. So, 0 must be in the set. 1 has to be in the set. I think by symmetry, since y minus x uh, is equal to, let's say, any number now, any z plus, right? Any a, x minus y must also be something, and it's going to be equal to minus a, right? So by symmetry, minus a must be contained in the set if a is. So yeah, this argument isn't the best, but with when we're studying integers in the next section, we will see how this works a lot better. But yeah, ultimately it's an inductive set and it contains the negatives and contains 0. So y must minus x has to belong to z and it can be anything in there. So S prime indeed is the intersection of all of them. An example of equivalence relation that contains S but isn't S prime would be y minus x belongs to what should I call it? So basically all integral multiples of half. I'm going to call it half z. So what does that look like? That means half minus half, 0, and so on. So it includes 1 here, right? So any set like that would be included in the equivalence. It would be an equivalence relation that contains S. And if S happened to equal 2 here, then we could change it to 2Z essentially. And you can, yeah. And 2Z is similar to half Z. I'm not even sure if half Z is a real thing actually. But yeah, half Z might actually be a Z half. I'm not sure if that's a thing. Maybe this is what it actually is. Yeah. So this is what it looks like. Okay, question 6. Yeah, now remember that equivalence relation on the parabolas, we can define an order on there too. And you'll see it's pretty similar to a dictionary order. So yeah, we have two parabolas. Now, if if the quantity, if the constant has happens to be what? So if y minus x naught, so I think if it's above, so if any parabola is above another, right? Then this a is greater than b in a sense. That's one thing. And if they're on the same parabola, then we have to check the x coordinate, I believe. Yeah, x naught is yeah. If x naught is less than x one, then so this point is less than this point. So essentially, it's like a dictionary order. You go to the highest parabola, you go along the whole. There is no highest parabola, but you get the idea. You go along the parabola and you check the x coordinates. Then you go to the next one, which would be, well, there's not exactly an x one either, but yeah, that's how you order it. hmm Now, yeah. So I described it geometrically just now, and we have to show it's an order relation. So essentially, an order relation behaves like a line, and you can kind of see how we're making the real R2 plane into a line. So what are we doing here exactly? Let's see. order relation is total. So between any 2 points. Let's say if the 2 points aren't equal, then yeah, for any 2 points, either this is a constant of 2 points, right? Yeah, and z minus omega square, w square. Yeah. So if they're equal, we have a case, and if one of them is greater or less than the other, we have a case. So, and why is that? Because these are real numbers, and real numbers are indeed ordered, right? Okay. So, we're done with one case. Now, if they're equal, that's another case you have to deal with. And if they're the by totality of x and w, we have another. We have the three cases for the whole coordinate. So essentially, we're using the totality of either a real constant of the whole term or the real constant of the one coordinate, and we're extending the totality to the entire plane. And yeah, and total is comparable. So I dealt with totality first. Let's do with antisymmetry. So yeah, if we're taking the same point, not only are these equal, but these are equal too. So we can't have that. So the order relation isn't satisfied, and non-reflexivity is satisfied this way. And for transitivity, we'll have to break it into cases. So if they're equal, then we compare this, and by transitivity of the real numbers, we're done. Uh, that would be in if, hang on. So there are multiple cases here. We need to compare the constants and then have transitivity there. We need to have the coordinates and then have transitivity there. But because we have transitivity over both of the separate orders, we have transitivity over the whole order. This is this will be the same motivation for the proof for why the dictionary order is in linear order. Yeah. So we'll have to do case work. There's no other way around it, I think. Okay, so what should we take? P and Q, I guess. So if they're all equal, then we check the coordinates essentially. If one of them is greater, then we've got the order with both of them, right? And so it's going to be either less than or greater than. We've got an order with both of them separately, and then we're going to compare these two. And yeah, so yeah, this should do it. Okay. Wait, what are we given exactly? Okay, so yeah. So one case won't happen here, right? So this is greater than this, and this is greater than, yeah, let's take this. Yeah. So if they're all equal, then we compare the x coordinates, and by transitivity of uh, q, yeah. So if they're both equal, then we compare this, and since if they happen to be equal, or the reverse order will in trouble because it's contradicting our original assumption, and yeah. So by transitivity of the real numbers, we can have the transitivity of this thing. And in the other case, with even one of them equal, we don't care here if one of them happens to be equal, and we'll have one order preserved because by transitivity of this, right? So if these are equal and this is the case, then this is y minus x square will be greater than something equals to z minus this way. And a similar thing if the other thing is equal. So in every case, y minus x square is either equal to p minus q with x greater than q, or it's greater than, and we don't care about the x coordinate. And this is essentially the same argument for a dictionary order. Will I do it now? I will not because it's casework and I hate casework. But yeah, the argument is this. I am, yeah, pretty sure. All right. Check that, show that the restriction of order relation is an order relation. How do we show that? I am tempted to skip it. I'll just write it down and see if it's the same argument. So yeah, so transitivity, the exact same argument holds, right? Now we have to check non-reflexibility. So yeah, so if X is not in the big set, then X will not be in the small set. Hang on, X comma X. In general, yeah. If A naught is a subset of A. This holds in generality because it's the contrapositive of what a subset means. And because of that, non-reflexibility is a trivial thing. Right. Now, yeah, so instead of using the property of the big set in the smaller set, what we're doing instead is just using set theory. So that changes the argument a slight bit, but essentially we're going from the big function to the restriction, and it's not in the big function, so it's not in the restriction for any member of A. Okay. Now, for A naught. Now, yeah, for comparability, the let us see. Is it similar to transitive? Let's see. So it must obviously belong to the small one, right? And since it belongs to the small one, we can compare it. And yeah, all ordered pairs are going to be in the small one. So wait, what if it by chance isn't? The only way it won't belong to it is if one of them is not in the small one. That's the only way it will happen. Because the restriction of the order is defined as A naught cross A naught, right? That's how it was defined. So if they happen to not be comparable, then what's actually happening is one of the sets is not in A naught, which is contradicting the assumption. So yeah, we'll be fine here too. Okay. Check that the relation defined in example 7 is an order relation. Yeah, it's similar to the one in question 6 actually. So there's not a major difference if you look at it carefully. Let's see. Yeah, it's borderline identical to the parabola. So essentially, yeah, so for any real number, you just bring it to the square. And what you're doing is you're going in a dictionary like this. So you're going here, and then here, and then here, and then here, and here, right? So what's the lowest here? The lowest number here is 0 because 0 is less than every square number, right? That's the lowest number ever. And every number greater than 0 is greater than 0. And this is another essentially dictionary order, but instead of going along each parabola, we're slicing along one parabola, which happens to be y is equal to x squared. So we're going here, 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 going as we're going down, right? That's pretty much what the dictionary order is, what the order is, and we're squeezing the entire real line onto the parabola. That's what it is geometrically, and I am how do we show it's an order relation? Yeah, so I think it directly follows from showing that it's a dictionary order, right? If dictionary orders are directly shown, then this is also shown. And I'm not doing dictionary orders, so yeah. hmm Okay, we have to show that this map is order preserving. That should be simple. Okay, I'll take a break. Yeah.